Hello all, we will look at a problem of water supply management. There is a set of cities that needs to be supplied water from a set of reservoirs through pumping stations. Each reservoir has a availability. Each pipe has a capacity to carry water, and each city has a demand that need to be satisfied. We need to maximize the amount of flow of water to the cities. The availability of water from the reservoirs is in thousands of cubic meter per hour. The reservoir 1 has the availability of water for 35 thousands of cubic meters, and for reservoir 2 it is 25 thousands of cubic meters per hour. The capacity of each pipe is indicated in thousands of cubic meters per hour in this diagram. So this diagram depicts the reservoirs, the intermediate pipelines. There are nodes and then the final cities that the water needs to be supplied to. This study needs to be undertaken to find out if the existing network will be able to satisfy the demands of the cities in a 10-year time span with 18, 15 and 20 thousands of cubic meter per hour requirement. The capacities of each pipeline between the reservoirs and the nodes are indicated above the arcs.
Now we solve the problem in this way, where we have the inputs of the entire distribution network, and then we click on solve, which invokes the Python program to optimize the problem of water supply management, and we get the output where it shows the flow in each of the network and how much it is able to satisfy out of the entire demand. So if we see, the reservoir 2 is able to satisfy the network out of 22 units, it is able to satisfy 15. However, in the final cities, we see that the city 1's requirement of 18 units is being satisfied to 17, and 15 units of city 2 is being satisfied, whereas in city 3, the 20 units is satisfied.
Now we formulate the model by transforming the graph with a fictitious source node and a node with where all the cities are connected, which we call the sink. So we have a set of nodes, the arcs between the nodes, and then the capacity. The source is node 11 and the sink is made node 12. So we want to maximize the flow of water to the sink while the demand constraints are satisfied. The same network is depicted here, where we depict 11 as the source node and then 12 as the destination or sink. And we represent the amount of flow from the cities to the node as the city's requirement. We declare the sets, parameters and the variables. So let's say that I is the set of all nodes and A is the set of the arcs between the nodes. The variable x is defined to know the amount of water passing from node I to j. The parameter capacity is declared indexed by the nodes to define the capacity of each arc. Now we define the constraint and objective. The first constraint is that the total amount of flow going into a node should be equal to the total amount of flow out of the node if the node is not either of source or the sink. We define the second constraint as the amount of water that flows in each of the arcs. The sum of that amount should be less than the capacity of each arc. The objective is to maximize the amount of water going into the sink. We define the data where we define the set of nodes, the set of source. So the set source is that of out of these nodes, the source is 11 and then the sink is 12. The set of arc is that one arc is going from 11 to 1, which is from the source to the reservoir 1, and then source to reservoir 2. Then source to from reservoir 1 to node 3, reservoir 1 to node 5, and reservoir 1 to node 6. We can verify this. So from the previous diagram, we see that from reservoir 1 to 3, 1 to 5, and 1 to 6. Similarly, 2 to 5 and 2 to 6. So that's how we are defining the arcs, and the capacity of each arc is defined by the parameter capacity.
In the next video, we will see how to implement this problem in Pyomo.
We save two files, one is the py file and one is the data file. We can define this in the data file. Now we first start the py file with importing the environment. We define the capacity. Now we define the variable of amount of flow, which is indexed by the nodes. And the objective would be to define the maximum sum of all the flows in the node 12, which is a sink. We make the sense as maximize because we want to maximize the total flow to the sink. Now we define the first constraint. And this would be only applicable when the node is not within the source node or the destination node. We define the capacity constraint. As the name of the data file. So now the model is built and the solver is created. Pass the model into the solver. And we want to see which are the arcs where and what is the amount of flow that the solver is suggesting. So we will iterate through the arcs. What we see here as the output is given and the total volume of flow through the network is also given. So when we construct this as the output, and we can see the result what the model has suggested. So it suggests the volume out of the total capacity in the node. So the reservoir 1 had the capacity of 35 and the 2 had 25. The node 3 had a capacity, the arc between node 3 and reservoir 1 had the capacity of 25. Similarly, 15 was the capacity for the pipeline between node 3 and 4. And then the requirement at city 1 was 18, and then in city 9, in city 2 it was 15, and city 3 it was 20. And we see that the solver suggests that the flow that is happening between the source and the reservoir 1 is 31, the source and the reservoir 2 is 21 out of the 25 capacity. From reservoir 1 to node 3 is 16 out of the 20 capacity. Node 1, reservoir 1 to 5 is 15, it's utilizing the full capacity. And then finally we see that the total requirement was 18,000 cubic meter per hour for city 1. However, the network only is able to satisfy 17,000 cubic meter. So the conclusion is that the current setup is not able to satisfy the requirement of city 1. So this concludes our tutorial on the water supply management implementation.